So thank you very much for braving the storm, staying here as late today as on a normal day. It's a pleasure to be able to welcome and introduce Aaron Parsons as today's speaker. Aaron comes to us from Berkeley. He teaches at Berkeley, and prior to that had been a Towns Fellow and an NSF Fellow at Berkeley and a grad student at Berkeley. Where, oddly enough, he spent a great deal of time at Arecibo, thousands of miles away from his advisor, but somehow that worked out, and brilliantly, in fact. And he made it to Berkeley from Harvard, where, as we learned at the ITC luncheon today, he learned some of his, I guess, first formal training in electronics was from Paul Horowitz, so there are a great many careers launched from Paul's lab. The background for what Aaron's going to be discussing today, I suppose, might nearsightedly, I guess I'd say, begins in the early 2000s with some seminal theory papers. Avi and Lars, for instance, were leaders in that. And then the instrumentalists jumped in and thought, well, we can detect that pretty easily. And now, about 10 years later, we're still trying. One of the forefront efforts, though, is what Aaron will be discussing. That is the instrument paper and its descendant that we hope is going to be built in the coming few years. So Aaron got into this field fairly early. He was paper was his graduate thesis, and so he's really he's riding a wave and will carry us through, and him for another 10 and 20 years, we hope. So without putting undue pressure on Aaron, I just thought that I would note that among the many instruments that are out there, this is, of course, a completely objective comment, of the many instruments that are out there, paper is truly at the forefront of those, and I would say is most likely to make the detection of perhaps the 21 centimeter line at, say, a Z of 8 to 10. It'll probably make it first, and now hear the pressure. Probably make it in the next 12 to 18 months.
Wow.
We'll see. Anyway, thank you very much, Aaron.
Thank you, Lincoln. Hope I can live up to those expectations. We'll be working really hard. I'd like to reiterate thanks for joining me on this cold, wet day. I was going to talk a little bit about this experiment I've been working on, paper, the precision array to probe the epoch of reionization, and kind of where it's headed. And it gets its name, paper. The acronym was cooked up by my mentor, Don Backer, who, when we were first getting started, as Lincoln was saying, we're experimentalists, we're just going to rush out there, we were just going to do this. He said, all you need to do this are PAPERclips and a supercomputer. Our expectations have been tempered a little bit in the decade that ensued, but I still like that quote, and I find ways to put PAPERclips into the telescopes that we're continuing to build. So what is this epoch of reionization that we are after here? Well, so this is a plot lifted from one of Avi's Scientific American articles, color-coded, to show that on the left-hand side there we have, off the edge of the page, the Big Bang. We have this plasma that expanded and eventually cooled enough that the cosmic microwave background photons decoupled from the protons and electrons, which coalesced into neutral hydrogen. And so then we have the beginning of what is sometimes called the dark ages, where all the light that was left in the universe was basically this cosmic microwave background light. And all the gas in the universe, which was mostly hydrogen, was slowly falling under gravitational collapse to form the first structures. And for quite a while was actually tied to the cosmic microwave background temperature. So there was literally no contrast that you could observe in the true dark ages. But towards the end of the dark ages, you have the first luminous sources that start appearing. And those start heating the surrounding gas, The first luminous sources were probably very short-lived, so they were these very massive structures that needed that mass in order to cool effectively. And so you have these first very high massive stars that form. They explode shortly thereafter. They seed metals into the surrounding gas, which makes cooling more effective so that more star formation can go on. And eventually, you have quite a few sources that are all lit up simultaneously. And these sources are emitting ultraviolet photons, which go out into the surrounding medium and start ionizing the very gas that all this was forming out of. And so we went from, in the beginning, a predominantly neutral universe to what we observe today, where in between galaxies, the intergalactic medium is very highly ionized. So it's posited that there was this epoch of reionization, which was kind of this kind of rapid transition from a predominantly neutral universe to a predominantly ionized universe. And we would like to see the bubbles, the Stromgen spheres that expand around these first luminous sources and ionize away the intergalactic medium. So that's what we're after. There are a few ways to access this time in our universe. One is to look at high redshift quasars, look at these high redshift galaxies, and look for the Gunn-Peterson effect, which is looking at the resonant Lyman-alpha transition and watching it try to get flatlined as all of that emission is absorbed by any neutral hydrogen that stands between us and that quasar. And so as we look at higher and higher redshifts, trying to see quasars farther and farther back in time, we try to find the point at which the optical depth at the Lyman-alpha transition jumps up suddenly. And that would be a sign that there is some neutral hydrogen between us and them, so a sign that the intergalactic medium might not be 100% ionized. And in fact, we've started to observe this around redshift 6, a kind of sudden step up in the optical depth to the Lyman-alpha emission of these high redshift quasars. But the problem is that does flatline the emission of these background sources. That once you get to substantial optical depths of say 4 or 5, it really becomes difficult to see very much further than that. You start working in the wings of your Lyman-alpha transition, and it gets hard to infer what's going on. And the other part of this is that it doesn't take much hydrogen to hit these high optical depths at such a resonant transition. So using these high redshift galaxies, it's hard to see deep into reionization. You might get the last vestiges of it, but it's hard to see kind of what was going on during reionization. Similarly, we can use the cosmic microwave background and other kind of higher order statistics of the cosmic microwave background to probe the electron column density between us and the cosmic microwave background. And you can get this from polarization. You can get this from the kinetic and thermal Sanyel-Zeldovich effects. And this can also tell you, by inferring the number of electrons between us and the CMB, it's telling you something about the ionization state of the intergalactic medium. Are there electrons, or are they bound up in hydrogen? And so using that, you can infer, if you assume a model of reionization, suppose it were instantaneous, supposing the intergalactic medium suddenly goes from completely neutral to completely ionized, then you could just directly infer a redshift at which that would have had to have happened, given our precision cosmology as we understand it. That redshift would be something like 10.4, but it's very model dependent. And in fact, we know that reionization wasn't instantaneous. And so then you start having to adopt different models that allow you to infer when reionization happens. And so similarly, cosmic microwave background can probe the epoch of reionization a little bit, but it's an integral measure, and it's hard to kind of get the play-by-play of what was happening there. So here's back to the Lyman-alpha transition. Here's a nice simulation, if it wants to play. There we go. That Nick Gnaden put out several years ago, simulating a box. So this is a fixed box in the of structure observe through Lymanalpha, where color now encodes temperature, and we are playing through time as we get the ionization state of the intergalactic medium. So the idea is if you were observing in Lymanalpha, that through all of this, we're basically seeing a black box. And we've taken a cut through the black box so that you can see kind of the edges in the holes. But you aren't going to be able to see through it if you enclose this box in the rest of the intergalactic medium that was out there. You won't be able to actually see through it to see the quasars that are living in these filaments here until kind of the last vestiges, not even here. I would say more like in the very last transition right about now. That's when you would be able to actually see through the intergalactic medium to actually see the background sources here at the Lymanalpha transition. And so, this is kind of illustrating how difficult it is to see back into the epoch of reionization. But Lymanalpha isn't the only transition of neutral hydrogen. We have another transition, the 21 centimeter transition, that we potentially could work with. So where we were previously having problems of getting to optical depths, to high optical depths too quickly for the amount of hydrogen that's out there, 21 centimeter as a hyperfine transition. It goes from the spin states of the proton and electron going from aligned to anti-aligned. The energy difference is very small. The radiation from this is at 1.4 gigahertz. It's 21 centimeters long, the wavelength of it. It's a very weak transition. For hydrogen, this only happens if you put an excited atom out there. It would only happen, it would decay with kind of a half-life of 10 million years. So very rare that it happens, but it's a weak transition. And what that enables you to do, now if you were able to observe the same simulation at 21 centimeter, you'll see that you can actually see through the whole box almost the entire time. That you never hit optical depth of unity in this transition at all. So you can see through the entire box. You can see all the bubbles forming, all of the heating happening. You can see the ionization bubbles that start forming around things. You can imagine making maps of this as it ionizes away and get a very nice play-by-play of the whole reionization process through here, which is great. The caveat is you picked a really weak transition, which means your signal now is correspondingly weaker, and you start having to come up with the collecting area and the systematics, control of your systematics and your foregrounds in order to be able to see that. But the principle of it is that because this is a line transition, so it was originally at 1.4 gigahertz, but redshifted to, say, redshift 9, that would be 140 megahertz. And each different frequency that you could imagine making your measurement at would correspond to a different redshift back in time. And so as the intergalactic medium has bubbles that, of ionization that grow and fade but eventually intersect and get bigger and bigger and ionize, you could imagine making maps at every different frequency of your array corresponding to different redshifts that would then map reionization. However, it's hard to make images of such high fidelity, and it requires a lot of sensitivity. So another thing you could imagine doing is using those measurements at different redshifts and at different angles on the sky to construct power spectra, where power spectra being the Fourier transform of this three-dimensional space that you're observing, where two dimensions are on the sky, and the third dimension is your frequency mapping to kind of line of sight distance. You could compute three-dimensional power spectra that probe statistically the ionization state and the size of bubbles throughout reionization. So shown on the top here are some simulations of kind of a fiducial reionization simulation, beginning at higher redshift with kind of the yellow line there, where most of the power is at high K modes, which is the Fourier transform of a real space length, which is to say that it's small bubbles. So most of the power is in small bubbles. And then as reionization progresses, you'll see that this power kind of walks out towards lower and lower K, so larger and larger spatial modes there, before the whole power spectrum then eventually at the end kind of just falls off the page here because you don't have the gas that's actually emitting the signal anymore. So eventually we'd love to make images of this, but in the interim we'll focus on making power spectral measurements because we'll have the sensitivity to do that sooner, and we'd like to see this evolution through time at different redshifts of where the power is going towards lower and lower K modes, and then try to find the rise and fall in the power spectrum domain. So now I wanted to talk about the specific experiment that we've been focusing on to do this, which is paper. So paper currently consists of 128 of these things. These are dipole elements. They're about the size of a picnic table. This is a cute picture that was made just a couple weeks ago by an actual real photographer, and you can see the difference. I think they did this kind of light painting technique where they take many exposures with light shining at from different directions. So in the middle here, we have this cross dipole element in a sandwich between two metal plates. And this is kind of a variation of a sleeve dipole design that allows you to have a broad frequency sensitivity with a dipole. This was designed by Rich Bradley at NRAO, who is, along with me, PI of the paper project. And this whole thing is enclosed in this kind of basket, which is meant to approximate a corner cube reflector for two polarizations, where you can expand the collecting area of this element by adding in these panels. And this whole element was optimized such that at different frequencies, we have 138, 156, and 174 megahertz, that the beam pattern on the sky was meant to not evolve very quickly. So the idea was, if we're going to have to differentiate our foregrounds from the reionization signal that we're after, we want to have a lot of control over our system, so we want to keep it very stable as a function of frequency and spatially. So this was kind of the beginning designs of paper here. Where I got my start on paper was actually on the electronics side. Remember, Don in the beginning said all you need are paperclips and a supercomputer. Well, that was our paperclip. But now we needed the supercomputer, the signal processor that would take the signals from all the different antennas, digitize them, cross-multiply every pair of antennas over a wide bandwidth, and produce the spectra that was required. So my start was actually in laying out that board there at the top left, which was Serendip 5. And then it's got a specialized processor on it called a FPGA, a field programmable gate array. And these things are these massively parallel processors. They process a lot of data in parallel, but they're very hard to program. So the other part of what I was doing was developing these software libraries that would allow you to kind of program them with fast Fourier transforms and cross-correlation libraries and things like that easily, where you could just tweak some knobs and say, I want 1,000 channels or 2,000 channels, and not have to redesign everything as he did that. And the idea of it was that then we could, if we're lucky, be able to upgrade our technology to adopt new processors. And Moore's law dictates that you'll have a processor that's twice as capable every 18 months here, that we wouldn't have to recompile everything. We wouldn't have to rewrite everything anyway. We could just turn a few knobs and recompile. And that was ideally how it would work. In practice, it's a bit more work to adopt a new generation. But the other thing we did was we got a huge community working together on this stuff, so that we could all be working on the same board and debugging it and getting the latest libraries working on it. And then we'll all use it flexibly to do our own different analysis. And so now Casper, which is what we call our group, the Collaboration for Astronomy, Signal Processing, and Electronics Research, is a pan-global collaboration with people all over the place. And I think these days you'd be hard-pressed to find a radio telescope that you don't see some of these boards on. And then for a brief history of paper, so I started as a graduate student in 2004 as we were just building our first 4 elements out in Green Bank, West Virginia, at the NRAO site there. We spent our time debugging these early systems, our 4-element and our 8-element system there. So paper in Green Bank is PGB, so PGB4. We spent a couple years going through that, learning what we could from our electronics. We've upgraded almost every element of the system. We've even upgraded the elements in the system, the antennas. You can see we have a much more refined dipole design here. We added the flaps. We discovered that that was something we could do without incurring any troublesome systematics. So So things really started getting excited in 2009 when we had our first deployment in South Africa. Paper in South Africa is PSA 16. And since then, we've been doubling the size of our array every year. And in terms of signal processing, what we need to do, that's a factor of 4, because it goes quadratically with the number of antennas. So we've been quadrupling the size of our correlator every year for 5 years running. And we are now finally at 128 elements dual polarization, which is what we're observing with right now. So I mentioned we're in South Africa. We're in the Karoo Desert, which is you fly into Cape Town, you drive 9 hours out into the middle of the nowhere. It's really, you couldn't imagine a place more desolate than this. You can kind of zoom in on Google Maps all the way, and eventually you end up with this really dry, deserty terrain. Nobody lives out there. But this is the site that was selected for the square kilometer array mid-frequency project, which will be kind of constructed out there. And in the meantime, while they built all this infrastructure, we figured we'd hop on over here where Paper is and use some of their network and power infrastructure for our own project here. And I'll talk a little bit about the next succeeding project, HERA, that will succeed Paper. And we're in the process of picking a location for that. And currently, we're looking at that hexagon over there. So why are we out in such the middle of nowhere? Well, so here's a spectrum, a dynamic spectrum, where we have time on the y-axis and frequency between 100 and 200 megahertz on the x-axis, taken in Green Bank, West Virginia, which is a protected radio quiet zone. This is one of the quietest places you can be for radio observations in the United States. And you see all sorts of stuff out there. There's, on the left-hand side, there are aircraft bands that are in there. At 137 megahertz, there's Orbcomm satellite transmissions. There's a couple other random stuff. This right here is digital TV, which is really awful. It occupies wide bandwidths. So this is all terrible stuff. And every frequency that you chop out here is a redshift that you don't get. Right? So frequency matters, and it matters a lot. So every time you cut a hole in your band, that's something that you'd really prefer not to do. South Africa, in contrast, you can see over the course of nearly a whole day is beautiful. There's nothing. It's wonderful. The only thing that you see is this, which is that Orbcomm satellite again. You just can't run away from satellites. But other than that, it's a beautiful band. So that's why we're in South Africa. So we decided to go out there in 2009. They rapidly bulldozed an area out there. We shipped the antennas down. And within a month, had our first fringes on the system. That's them up there. And then later, as we've gotten better and better at building out, we've incorporated interns from local technical universities like University of Durban to help us build things, help teach people how these systems operate and the principles of RF electronics and astronomy. And you know, we make pretty maps with that stuff. So here's a picture of our 32 element array out there. In the center is where we put that supercomputer, the correlator. Over there, there's a backhoe kind of for scale over there. And you can see the antennas are all over the place. And with them, we make beautiful pictures of the sky. So here, you know, this is done with an interferometer, so it really emphasizes the kind of point source structure on the sky. So you see a lot of point sources around. That's Centaurus A in the middle. Centaurus A, it's a nearby galaxy, but what you're seeing there isn't like the side of the galaxy. The galaxy is actually perpendicular to that. What you're seeing are the outflows from the presumably massive black hole in the center. These jets coming out of it out there. There's a cool little supernova remnant over here. You don't see the face of the supernova remnant shell because it's pretty thin, but along the edges of it, you see through a longer column of electrons. So you see, it kind of emphasizes the shell there. And then here is the Milky Way, the galactic plane. We're not, with our interferometer, sensitive to the overall shape of it, but what you can see are the supernova remnants that are dotted all along the galactic plane there. So this is all fun, beautiful stuff that is totally in the way of the experiment that we actually want to do, right? This is all nonsense that we need to get rid of. So how do we do that? Well, for things like the cosmic microwave background, when you had an instrument that made maps at multiple frequencies, since you know that there's fundamentally one surface that you're trying to map here, the cosmic microwave background, you can use all those different measurements and frequency to control for your systematics. But for our experiment, it's a little harder because all of those different frequencies are actually different redshifts, which have different structure in them. So it's not the same literal signal. It's not a single surface. We have a 3D volume that we ultimately want to map. So how do you get rid of all this galactic structure out of this 3D volume that you'd like to be measuring? That's the great conundrum that's facing us in 21 centimeter intensity mapping experiments. And we don't have nearly the axes for control of that as you have in these cosmic microwave background experiments. So there are a couple different approaches. One way, so this is meant to illustrate where we actually sample our data. So our interferometer, when you take two antennas and you correlate them, you're not directly making an image of the sky. What you're doing is you're sampling a spatial Fourier mode of the sky. And we call those spatial Fourier mode, these angular Fourier modes, U and V. So that's what your interferometer samples. And then we can sample them at different frequencies. And every single frequency at every single separation, every single Fourier mode that we would measure has foregrounds in them, which are meant to be illustrated with the red here. So you have different options here. One thing you could imagine doing, and is often done in radio astronomy, is you undo the Fourier transform that your interferometer sampled. You Fourier transform U and V to the angular coordinates on the sky, and then you can make these nice pictures of actual sources, like what I just showed you, like Centaurus A or these supernova remnants, as they evolve versus frequency. And so one way of localizing your foregrounds is actually to localize them to the angular structures on the sky that you could imagine subtracting off those point sources or modeling them versus frequency and subtracting them off. But then you end up in image space. And like I said, the fundamental thing that we want to be doing in these first generation experiments is measuring the power spectrum of reionization, because it takes less sensitivity to be able to do that. So another thing you could imagine doing is saying, well, look, our interferometer already did two of our Fourier transforms for us. We took the Fourier transform of both sky angular coordinates. All we really need to do is take the Fourier transform of that last frequency component, and which frequency was line of sight, and so that turns it into an inverse length scale. And suddenly you have a three-dimensional Fourier cube over which you can compute power spectra. And so if you did that, you might ask, well, what happens to your foregrounds? Well, turns out that almost all of our foregrounds at these low frequencies are smooth spectrum. And they're smooth spectrum because a lot of this is synchrotron emission. It's just electrons spiraling around the magnetic field. And there's nothing that sharply differentiates one frequency from another frequency. They're just all part of a big power law of electron energy distributions out there. So almost all of these foregrounds are smooth spectrum, which means when you Fourier transform along frequency, they tend to pile up at the low Fourier modes. So one thing you could imagine doing is just don't use them. Use higher Fourier modes. And that, in a nutshell, is our big breakthrough. But I'll try to motivate it a little better than that. It turns out it's not quite as easy as that, because our instrument itself is chromatic. And so you're not able to take a Fourier transform directly along that frequency scale, because the Fourier modes that you measure are also frequency dependent. And that's a pain. Another way of saying that exact same thing is when you put two antennas on the ground and you put a source up in the sky, that source comes in as a plane wave, and it'll hit one antenna before it hits another antenna, right? This is the principle that you used when you do synthesis imaging. If you move that source on the sky, there will be a different delay between these antennas. It's a different phase versus frequency, and that allows you to localize structure on the sky. But I really want to emphasize that time delay, because when you Fourier transform frequency, what domain do you end up in? Time domain. So any delay that your signal has shows up as a sine wave in frequency. It's a fringe pattern versus frequency. And that, if you took the Fourier transform of frequency, localizes it at a particular delay. If you take the Fourier transform of a spectrum measured by two antennas, you end up with a delay. And they used to make correlators this way. They were called lag correlators. And not only that, if you put a smooth spectrum source on the sky, I've put 4 smooth spectrum sources up there, then you end up with these what are close to delta functions in delay space when you take the Fourier transform. And then as the sky rotates over, so this is a simulation of a full day, you can see those sources wag back and forth on the sky as they rise and set. And some sources that are circumpolar won't set at all, like the one there. The other thing, though, is if you have a source on the sky that's not smooth, then when you take the Fourier transform, it'll be centered at a delay, but it's convolved with something that isn't well localized, right? It's got these wings. So any guesses on where that funny, noisy source was in my simulation on the right? Yeah, it's there at the top. It's the thing that leaks outside of these dotted lines here. And what are those dotted lines? Those dotted lines were saying, well, what is the maximum delay I could possibly have for these 2 antennas? Well, it's when your plane wave comes in from the side and traverses the full length of that baseline. And you can just calculate what that is. It's the length of the baseline divided by the speed of light. So there's just a delay right there, the maximum thing you could possibly have. So you put those dotted lines in there, and you'll notice that in our simulation here, none of the smooth sources on the sky went outside of that range. The only thing that went outside of this range was the unsmooth source that I put up there, this kind of funny little source up here. So it turns out that almost everything on the sky is smooth. The only thing maybe that's unsmooth is reionization. We know reionization is not going to be smooth. So in some sense, what we need to do is find where these dotted lines are, which you can just calculate, throw it all away, and look outside of that. That's our foreground removal technique. And the longer the baseline is, the longer the separation between our 2 antennas, the wider the sky is distributed over, right? Because there's a longer time to go from one antenna to the other. So here's 4 different baseline lengths with the same sky and the same distribution. And you see how the sources get spread over a wider and wider delay range for longer baselines. So what this means is this. We wanted to take the Fourier transform of frequency because that gives us Fourier modes along the line of sight. It was the last axis we had to take the Fourier transform of to get power spectra. So in some ways, you can read this delay axis, if you wanted to, as a k-parallel, a Fourier mode along the line of sight. But foregrounds, because it's not truly a transform along just the frequency axis, because we have the smearing between the frequency and what Fourier mode we sampled, that the longer our baseline is, which baseline length is here on the x-axis, the larger the range in k-parallel that are occupied by foregrounds. And so this has been a big breakthrough in the community to get everybody to realize that there's a thing called the wedge. And the wedge is that the longer your antenna separation is, the more foreground contamination you have as a function of this line of sight k-parallel mode. And this isn't just a baseline by baseline problem. You can use all of the information in your array. This is something that a postdoc working with me, Adrian Liu, is currently working on. You can use all the information in your array in a full covariant analysis, optimal quadratic estimator formalism, and you still won't be able to invert out the window functions that bleed down to the low order modes where your foregrounds are occupied. So what this says is this is something fundamental in our measurements, that it's there on single baselines, which is kind of what I've talked about here, but it's there even in the whole array. And there's no way around this unless you are able to directly model those foregrounds and subtract them out. So we have a big question. Do we model these foregrounds and subtract them out, or do we just cut out the wedge? And what we've done with paper is we've just cut out the wedge. That's the easiest way. Someday we hope to be able to model them and remove them, but in the near term, we'll just, for however long our baseline is, we just chop out that range of foreground contamination. we've gone through and we've measured this experimentally. We get something. Here's the wedge you'd predict in white. And then as a function of our baseline length here, we show where the contamination walks out to. And you'll see it bleeds over a little bit beyond the horizon. And that's because there is some spectral variation actually on the sky. There is some. These aren't perfectly flat foreground sources. They have some slope. They have a little bit of structure. And that causes sources close to the horizon to bleed out a little bit. So you need to walk out just a little further. But after you walk out further, it's gorgeous, beautiful, no foregrounds. You get a drop of easily, here this shows directly 4 orders of magnitude. And it's noise dominated where it rolls off. So usually when you want to make pretty images of the sky with a radio interferometer, you scatter your antennas all over the place. You sample a lot of Fourier modes. This makes pretty pictures. But now we're realizing that all of these longer separations are worthless. You have to throw out so much K range that they're just not even worth measuring. So what would you do if they were worthless? And really, all you care about is using this frequency axis to get rid of your foregrounds. Well, you would actually pile your antennas kind of close together, as close as you might put them both horizontally and vertically. And then the only problem is we notice one thing on this wedge, which is that as you go to lower and lower, shorter and shorter separations, the sky is actually getting brighter. And that's because there's a big galactic synchrotron component that starts pushing you back. So there's kind of a sweet spot, say around, where is it? I think the sweet spot is about here, where there are diminishing returns for going much lower than that. So you pick that scale and you place your antennas on that scale. And the other cute thing you can do here is because 2 antennas measure a Fourier mode that is the vector separating them, if you lay them out this way, then you can pair different antennas and they're all sampling the same Fourier mode. So if your sensitivity is starved, if you can measure coherently the same Fourier mode over and over and over again, then you build your sensitivity faster than you would do incoherently if you sampled a bunch of different modes and had to square them before you combine them. So this was cool. This is what enables us to punch above our weight with paper. We have less collecting area than anybody else out there, but we place our samples carefully in the UV plane to get more sensitivity out of our array. So this was slightly annoying. We had laid them out all scattered across the field, and we had to enlist some people to help us to move them all. But another, on the flip side, our antennas aren't that big, so you get 4 strong people, and you lift them up, and you just carry them over there. And our cables all were above ground. So now our new antenna configuration is there, where you can see that they're all laid out in these kind of packed columns there on the top. And so now we're out of simulations. These are actual measurements now. So we placed all of these antennas in these kind of grids. And it turns out that now you only care about, there are only like 3 different baselines that you even care about in this array. And you've sampled them over and over and over again. So this is, and all of the different antennas that go into that, you just calibrate and then you sum them all up coherently. So we end up with something like this, where versus sidereal time on the vertical axis, and having done that Fourier transform of the frequency axis to get delay, we can do that, and we can see all of our foregrounds, and you can see how tightly bounded they are by the horizon there. It's beautiful. And this bleeding out that you see is mostly because we had to cut out some of that Orbcomm satellite that was in our band. So once you filter out these modes and you compensate for that kind of lost information, it's all noise. It's beautiful. And notice the scale here in temperature. These are technical well, I think these are in Janskys. So these aren't temperature, but Janskys are proportional to temperature. So you can literally see this was 4 orders of magnitude in temperature, just gone. In power spectrum space, where everything's plotted in temperature squared, that's 8 orders of magnitude, just gone. And we're noise dominated. So this is very exciting. This is what it looks like in the opposite domain, in frequency domain. This is what all those foregrounds looked like before we did that filter. This is what it looks like after. So this is where we are with paper. You can take these handful of baselines that we even care about. You can do that delay spectrum. You can, within the horizon here, you integrate over the time now. You can extract what the foregrounds were before you filtered them out. And then you filter them out, and then you look at what was left after you filtered them out. And the answer is it's pretty close. It's way down there, 8 orders of magnitude. And you translate that into cosmological units where you can plot the theory curves, and you'll see that compared to the previous best results, we've improved by almost, we'll call it 1.5 orders of magnitude there. And we have maybe 2 orders of magnitude to go before we're ruling out vanilla reionization or detecting vanilla reionization models. The other thing you could imagine doing is, so this is a vanilla reionization model here, but what this is, it's a product of a shape that is the ionization field and the brightness temperature of the gas. And so you can imagine asking, well, how well do we really know that brightness temperature? If the brightness temperature were much higher, you could scale this thing up. And the units on this are temperature squared. So you don't have to scale it up much to get this to move. You would scale this up maybe an order of magnitude, and you'd be up here. So what kind of things can do that? Well, so this is a plot from Pritchard and Loeb, 2012, showing the history of that brightness temperature expected versus frequency. And there are a few different scenarios here, depending on some of the physics of what's going on here. Some of these bumps are unambiguous, that involve first collisional coupling of the spin temperature of 21 centimeter to the gas temperature, which causes an absorption trough relative to the CMB. Then the second trough is this kind of bizarre Waldhausen field effect coupling, where once you have Lymanalpha photons floating around from the first star formation, those Lymanalpha photons establish a color temperature that excites the hydrogen atom to an excited state, and then it drops back down preferentially into the excited 21 centimeter state. It's kind of a bizarre walk through the graph of the different transitions that are available to you. Any case, you get another dip in the brightness temperature. And then in these models, what brings it back up is the feedback of the heating into the intergalactic medium, combined with some heating from these X-ray binaries that have emission that can penetrate deeply into the gas and get farther away from the sources of these photons before they kind of dissipate into the heat of the intergalactic medium. But if you took that away and said, look, suppose there were no X-ray binaries out there, no X-ray emission penetrating deep into this, you can get these large absorption, the brightness temperature going into a large absorption. And so you can translate our upper limit to a limit of absorption there. And you can just say, look, the brightness temperature couldn't have been a higher contrast than, I think it was 220 millikelvin. Otherwise, we would have detected the power spectrum that results from it. If it got that cold and then ionization, the ionization front started going through here. So this may not surprise theorists who said, yeah, of course you got to include X-ray binaries in your simulation. But as I said at lunch, you don't know what you think you know until you measure it. All right, so then I was just going to fast forward. We put that, these limits were with 32 antennas. We now have 128 antennas out there, so 4 times the sensitivity. So we're excited about that. Observations are ongoing. We did a lot of work. We built a nice correlator. We shipped it down there, and then the shipper told us that a mini tornado struck their shipping truck. And somehow these correlator components that we had floated off the back of the truck and got some tire marks on them, which you can kind of see up there. So this was a big problem. But fortunately, because Casper was so successful, people in South Africa had the very boards that we built these correlators out of, and we could ask, can we please borrow yours and we'll replace them, promise in a month's time, and they took us up on that. And so due to that and the heroics of our own Dave McMahon at Radio Astronomy Lab at Berkeley, we have a full 128 dual polarization correlator out there and running. And I should point out, so the FPGA stuff is all over here. We now use graphics processors, these graphics cards, to do the cross-correlation analysis. And they are running code that Lincoln developed with Mike Clark here, which turns out to be a very efficient way. There's a whole lot of computational power bound up in those graphics cards. So it appears to be, for now, the most efficient way to build these large correlators. So we have a large deployment out there. We're at 128 now. Last season was 64. We're analyzing that data. We're very proud of that. We went 172 days uninterrupted observing with that thing. We didn't have to do a thing. It was amazing. You flip the correlator on and you walk away, and 172 days later, we finally said, hey, we might as well turn it off. And that's what we did. So why is paper doing so well? It's kind of weird. If you look in terms of collecting area, paper's built, MWA is built, LOFAR is built, SK-LO is still a to-be-built instrument. But you can use fiducial numbers for what these areas are. And you can see we're low. So how are we doing so well? Well, one was the trick that I told you about, that we redundantly sample the same modes over and over and over again. That allows us to build sensitivity a little faster. And the other is where we've placed our baselines, because not all baselines are created equal. Long baselines don't give you nearly the sensitivity that short baselines do. And we've put ours very close together. And so then you can say you can take different forecasts of where the foregrounds are. The pessimistic forecast is basically saying that foregrounds leak out a fixed width outside of the horizon that we've kind of determined empirically for paper. Then you could take a more moderate forecast that allows you to do some suppression and working closer to the edge of the wedge that get you kind of to the horizon limit or to the edge of your beam, which for paper is about the same, but it's not necessarily the same for some of these larger elements. And then you can take an optimistic scenario that says, what if we can model and subtract all of these foregrounds even within the wedge? Then what kind of sensitivity would we get towards a fiducial reionization scenario? This was work that was done by Jonathan Pober in a recent paper for next generation 21 centimeter arrays. And as you can see, kind of uniquely of all of these instruments here, HERA paper is one where our signal to noise doesn't really change depending on these pessimistic versus moderate scenarios. And that's a function of where we've placed our baselines. But then you can see once you go into the kind of more optimistic regimes that collecting area really comes into play. And then we can no longer bat above our weight as much. Although we still managed to edge out the MWA just because we did the redundant trick. Just to emphasize here, so here's a simulation of the wedge for a much larger dish. And the point of this was, remember this wedge, which was baseline length and Fourier scale on the y-axis, that you can lay over contours in power spectrum space. This is like a 2D cut through your power spectrum cube, your 3D Fourier cube. And theorists plot these in very misleading units called delta squared, which is k cubed times the actual power spectrum. And you're measuring the actual power spectrum with this thing. So if you undo that k cubed to plot signal contours in actual p of k, you'll see that through gradations of orders of magnitude here, these are dropping by orders of magnitude very quickly as a function of baseline length. So if you have to have a longer baseline and have to throw out all of these Fourier modes before you get up here, you've necessarily walked yourself down in signal amplitude 3 orders of magnitude. So this really says if you want to build sensitivity fast, you really need shorter baselines. You really need it. So if you knew all of this from the start, we started paper a decade ago, but if you knew all of this from the start, what would you do the second time around? And that is the question that we're trying to answer right now. And we think that the answer is HERA, the hydrogen epicyclic ionization array. We need collecting area with paper. We're sensitivity bound right now. And these dishes that we've designed deliver 20 times the sensitivity of each paper element. So you could replace the existing paper with 128 of these, and I think you'd have a detection pretty easily. And if you even up the number of these, then you could really imagine doing not just detection and kind of basics, but you could really get really deeply into high significance probes of the power spectrum. So we've been putting together the team that'll do this. I'm leading it. We're involving a lot of different institutions directly under a proposal that's going into the Mid-Scale Innovations Program. We're one of 12 in the final round of this selection. We also have collaborators at Cavendish, at University of KwaZulu-Natal in South Africa, the South African SKA, and not listed on here, but is also the Academica Sinica Institute in Asia A in Taiwan is probably joining on as well. And this is managed by Dave DeBoer, also at Berkeley, who has a lot of experience with ASCAP in Australia, managing that project. So you put HERA in here as we're designing it with 331 is our current number of hexagonal packed dishes. And you'll see that just sheer collecting area wise, we come in somewhere between LOFAR and SKA. And my argument is just looking at collecting areas, you know something has to come in there just to bridge the gap before we jump into SKA low here. Even under pessimistic scenarios, this thing is designed to succeed even under pessimistic foreground scenarios where we don't do anything other than exactly what I've showed you here. You can get almost a 20 sigma detection just by that. If you can do a moderate foreground removal, you'll see similar in the paper sense. The significance goes up a little, but not a lot. And if you can somehow manage to get rid of all your foregrounds, your significance goes way up. So what we'd like to do is build this thing, promise that we're going to do some cool science with 20 sigma detections, and work hard on our foreground removal image-based modeling and removing of these foregrounds to really unlock even more science with this project. This is the dish that we want to use. It looks all fancy when you simulate it with kind of glossy things, but this is wire mesh, PVC pipe, concrete hubs, telephone poles, and wood. This isn't meant to last a lifetime. This is an experiment. It's got a finite lifetime of 5 years. It needs to work nicely for 5 years and not degrade. But all of these things meet those specifications. And the other thing that it has to do is not reflect signals around too much. So you'll see that there are these screens that are meant to insulate this dish. I've removed the screens here so you can see down into it. But there's screens that isolate these dishes from one another. There's a little splash cone here that prevents resonances between the feed and the bottom of the dish so that it scatters it out and back up onto the sky. And it's got a short focal height that means that for even reflections that do happen, it can go through several reflections up and back before the time scale of that is enough to move foregrounds out beyond the horizon. So this is optimized for that frequency domain removal of foregrounds. We've started building these. Carl Hylas, our esteemed director of the radio astronomy lab at Berkeley, has agreed to give us his backyard to build this thing. His wife gets to turn it into art when we're done. And these are literally telephone poles. We've built a concrete hub here. And you can see it's kind of inspired by my time at Arecibo. It's got these 3 poles and the feed suspended out there over in the middle. And Jonathan Pober, as I mentioned, has done simulations for these and for existing arrays, showing the significances that you can get for detections under pessimistic model, moderate, and optimistic models at various redshifts through this. And then he's also parameterized a simulation 21 cm fast in terms of 3 kind of core parameters. Let me see them. C here is the ionization efficiency. R is the mean free path of these Lymanalpha photons through the intergalactic medium. And T virial is the minimum temperature at which these halos cool efficiently enough that they can form the first ionizing structures. And so these three parameters kind of encompass most of the knobs that you can turn in a reionization model. And then what you can do is see in the effect that they have on the power spectrum compared to our constraints on that, how well can we constrain these? And these all, so these are the contour plots for all pairs of these parameters, and comparing them for optimistic, which is the inner, moderate, and pessimistic values. And what you can kind of see is that we're going to get of order 5 to 10% constraints on these, which is better than theory is for the astrophysics of reionization right now. So after 10 years of thinking this was easy, and maybe it wasn't quite as easy as we thought, we think that we have the instrument now that will finally turn the tables and toss the hot potato back to the theorists to start explaining what we measure. Using this, we can constrain the evolution of the ionization fraction versus redshift. I guess this is actually neutral fraction that we've plotted here through a fiducial simulation of reionization. So we can recover the ionization state very well throughout the history of reionization, not just at these late tails. And if we get our imaging algorithms and our foreground models working, then we'll actually be able to directly image these bubbles and start this next phase of moving beyond the power spectrum to directly imaging reionization. So to summarize, we think our foregrounds, fingers crossed still, are under control. We're currently sensitivity limited and integrating, and this wedge that we have empirically found in our data, we have good theoretical underpinnings for where it comes from. You can couple that directly into the design of your instrument, and it really changes how you approach these problems. Foreground removal within the wedge is still an unsolved problem. LOFAR is working hard at this. MWA is working hard at this. We're incorporating members of our team from MWA who will bring some of this expertise into HERA. But in the meantime, we have the techniques and the instrument to get a detection without relying on foreground removal within the wedge. Our current generation experiments will soon be at their sensitivity limits. We hope that PAPER will actually be able to get a detection out of what we're observing right now. It's going to be a close call. It may be a 2 sigma kind of thing, but who's going to believe a 2 sigma? It's going to be hard to vet that. We'd really like the instrument that will blow this wide open. Theory's been waiting on us for about a decade. We're sorry about that. But HERA, this next instrument, which we will, if we get funded in the MSIP, we'll start building this fall. And we'll see first light 2 years from that. And we'll have the full array up 3 years from that. We will get the kind of constraints on these reionization parameters that will flip the tables around on theory. Thank you.
Well, thank you very much, Aaron. We have good time for questions, so fire away.
What's the primary beam of a HERA antenna? It's about 3 degrees or 4 degrees?
Oh, that's about 10.
10
degrees.
Oh.
These are 14-meter dishes across and 2-meter wavelengths. And they don't point, as you may have noticed. So we got to choose the latitude that works for pointing straight up. And turns out where we are in South Africa at minus 30 depth, minus 30 latitude, gives us a nice cut.
So, I mean, I can imagine foreground removal working, killing things by, 4 or 5 orders of magnitude, maybe not, however, the 10 or whatever you need. So if you can...
If you're doing it in temperature units, we got 4 and close to 5, and all we need is 6.
So if you can say you hit a wall there, if you get most of the way there or halfway there, does that do you any good, or do you really need to completely eliminate them to improve your success?
So, so what are things that we worry about that could crop up there? I suppose you could imagine that your instrument itself is introducing the structure, but I think we've got a pretty good handle on what our instrument can even potentially kick up. And so I'm not worried about that. The last foreground that is just a risk that we have not quite retired yet is polarization leakage. And the idea there is if you put a polarized signal on the sky, all the observations we're trying to do are Stokes' eye. It's just total intensity, right? But if you put a polarized source up on the sky and you haven't perfectly formed your Stokes' eye, if you coupled a little Stokes Q into it, then because you have a different amount of phase rotation through a Faraday screen as a function of frequency, you can modulate the amplitude of your polarized signal as a function of frequency. And if you've coupled that into your Stokes' eye measurement, then that's potentially something that could kick up a foreground at these higher modes where we'd like to measure reionization. So that's the last thing we haven't retired, but we're close to retiring that. What you can do is try to measure Stokes Q directly and then infer the amount of leakage that could fold back into Stokes' eye. We're working on we have the measurements that do that. We're working on the analysis. We're really close to the level. We can right now rule that out down to the level of fiducial reionization models. If we can, and this is what we'd like for the paper, so this is why we're holding it up a little. If we can delve just a little bit deeper than that, then we can actually retire it as a risk that we can say, look, it's not even on the scale of what we can do with reionization. So I think that's the last foreground I'm worried about. Other than that, I think we've got a good bead on what our enemies are out there.
Is there a foreground where you have electronic noise in the first amplifier of one antenna and it transmits out of that antenna and leaks into the adjacent antenna and correlates?
Yes. So we call that crosstalk, and it can happen in a lot of different places. It can happen at the front. It can happen as you bring your signals back together and put them close together. It even happens kind of at the analog to digital converter where you've actually brought these quite close together. The nice thing about that is that noise does not change versus time. It's a static coupling, and so you can use the time variation of the sky to suppress that signal. And I didn't get a chance to talk about it in the main talk, but I just wanted to throw this out here. A new technique we're working on, which is really cute, is you can use the fact that as the sky rotates, different parts of the sky walk through your fringe pattern at different rates. So close to the pole, it moves almost not at all. As you get closer to the equator, it moves rapidly through your beam pattern. You can use this to actually use the time axis of your measurements to extract different regions of the sky. And so everything that's static in your instrument falls at the pole. It has no time structure. So you can actually just suppress that mode and then start looking. And so you can actually, in some ways, kind of contour your beam to match where your foregrounds are the best. But also, not all parts of your beam are equal. You get way more signal here than you do down here. So in principle, you should be weighting these by the response on different time scales that is optimal for a signal to noise. And you can do that on the very same data that I showed you already, and we get another factor of 3 improvement on our upper limits. But I'm working on that paper. Don't have it out yet.
Jonathan?
So just one point of clarification, you showed paper 32 data. Had you rearranged the array to the rectangular grid?
Yes.
For paper 32?
Yes.
And it's paper 128 now that you had.
Yes.
So that happened a couple of years ago, 2 years ago, whatever.
32 happened 2 seasons ago, 64 happened 1 season ago, and we're still working on the analysis of that. Every time you double the size of your array, you quadruple the amount of data.
Yeah.
So, and this is just walking through the data by itself. And so my student, Zaki Ali, is working hard on wading through that.
So just a follow-on question. It wasn't clear to me why the rectangular grid in one dimension had a different spacing to the other dimension. And HERA seems to be totally regular.
Yeah, so what we did with paper was our elements are quite small. And we said that there's a minimum scale that you wanted to go, that going shorter than that was not advantageous for foregrounds. And in fact, for what I just showed you about using the time axis to differentiate different parts are actually not advantageous, that you actually would like to keep them a certain distance apart. But then once you pick that distance, then you might as well populate it closely with these other elements. And one of the reasons is that we haven't exploited this yet, but we plan on doing it, that the one baseline that's straight across with a bit of a time lag will actually correlate with the signal that you measure over and up one. So that when the sky is over here, one baseline will measure that a Fourier mode. And when the sky rotates over, that same patch of sky will come into the other separation of antennas at sampling the same Fourier mode. So ideally, there's some extra redundancy that we could fold in to improve our sensitivity there. We haven't exploited that yet. But with HERA, we've already, part of the problem with paper is we didn't fill the space in between our antennas. That once you pick the scale that you want them separated, you might as well fill it in and get all the sensitivity that you possibly could from that measurement. And so with HERA, we've gone ahead and filled in that area. And now you're just trying to get 14-meter dishes as close together as they can. And that's what led to the hexagonal pattern.
Avi, for you?
It was like what he said. So actually, it's 14 meters, because that was not obvious.
Yeah.
And that's much larger than the wavelength we're after. So in fact, it's not like a field aperture. Your dipoles are separate, but much more than the wavelength.
That's true, yes. And so people who are used to making images with this will get a little twitchy when you start having these regularly spaced elements where you haven't subsampled your aperture and say, well, look, that's going to get grading lobes on the sky. That's absolutely true if you're making images, but we're not. We're doing Fourier mode analysis. That said, we would like to do some imaging, and so we may put in other additional elements around the edges that break with the grid to kind of give you more information about between the kind of sub-aperture information about what photons are doing.
Are there any remaining questions? If I may, I have one. The parameters in Kober et al. 2013b, that is the three parameters describing reionization.
Mm-hmm.
I was surprised not to see something about X-ray heating characteristics. I thought that was something that's relatively uncertain. Perhaps the comment is for much higher redshifts, but are there additional parameters that are also constrainable, even if not at 5%, that are fundamental?
That's a really interesting question. So for the heating of the gas, that's a pretty straightforward tweak to the amplitude of your power spectrum, and not. I think that the thought is that that's something that's kind of independent of the rest of the other parameters, and is just. You could almost tune it as more or less sensitivity of your array. So I think in that sense, for what Johnny was working on, it wasn't as interesting as these three parameters, which kind of got to the underlying power spectrum shape more and how well we could distinguish those shapes. Your other question?
No, that's good. If there are no other questions, let's thank Aaron again.